Okay, so we're going to look at the last example that said that there exists two prime numbers, P and Q, such that P minus Q equals 97. So we were disproving this, and so I mentioned in class how we could do this. So we could first say, notice, since P minus Q equals an odd number, P and Q must be different parities. I was going to say opposite, but then, yeah, I guess. So opposite parities. So let's say P is even, Q is odd. So this would be like case 1. Two is the only even prime, so P equals 2. Well, then P minus Q is equal to 2 minus Q, which is 97, which would imply that Q is what? Negative 95, right? Move the Q over there and the, yeah, negative 95. But, just as an example, 5 divides that, so not prime. All right, so they can't both be prime if P is even. So what about the second case? So case 2, Q is even, P is odd. In that case, Q is equal to 2, right? So P minus Q would be equal to P minus 2, and that's supposed to be 97, but that would imply that P is 99, and again, just to pick a number, I don't know, 9 or 3 or 11 or whatever you want to pick, 9 divides 99, so not prime. So then you can write a conclusion. Therefore, there do not exist two prime numbers. But so notice this one was a little longer, but it was still just a disproof, right? So now we're going to talk about Chapter 10. So Chapter 10 is mathematical induction, which is a huge concept. And I have an idea. So hold on one second. Can I pause the recording? Probably not. Okay, Okay, so now we're going to look at, see, I was hoping I could pull up a file. What's this one do? Oh, why are there selfies in there? Don't look at the selfies. Okay. All right, so let's look at, it didn't open. Do you see it? Where's it at? I'm picking it. You think I have to pause recording? Okay, is it recording? I guess it's recording. All right, so we're going to look at an example of mathematical induction. So we're going to look at, for every integer for every integer n that's a natural number, that was kind of weird, I didn't mean to write that. So for every natural number, you see what I wrote? For every integer that is a natural number, it follows that 1 to the third plus 2 to the third plus 3 to the third plus dot 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 up to n to the third. If you add these all up, it's really just n squared times n plus 1 squared divided by 4. So you don't have to add all these things up, you could just use that formula. So let's prove this. So there's really kind of 3 steps to doing a mathematical induction. If you look, they had 2, but that second one really kind of has 3 pieces. There's the assumption, the if part, and the then part. So for part 1, we're just going to show that it's true for the first one. So n equals 1 would be the first one. So we're going to let n equal 1. So we want to try to show that the left-hand side is the same as the right-hand side. So don't, Hannah, put the equal sign in, okay? Don't just plug a 1 in with the equal sign. Keep them separate, and you can use LHS for left-hand side. So I'm just going to write then left-hand side equals 1 to the third, which is 1. And the right-hand side would equal 1 squared times 1 plus 1 squared divided by 4, which is 1 times 2 squared over 4, which is equal to 4 over 4, which equals 1. So it's true. So it's true when n is 1. If you want to, you can plug in a 2 for the heck of it, but we don't have to. So the first step is to show that it's true for the first one. Now what we're going to do is our if-then part. So what we're trying to show now, and I'm just going to, you don't need to write this down, but we're going to try to show that this implies this. So I'm going to break this into 2 steps. I'm going to do the S sub k part in number 2, which is just our assumption. So we assume, so with any if-then statement, you assume the if, prove the then, right? So we're going to assume it's true for n equals some k that's bigger than 1, because we already showed that it's true for 1. So now I'm going to write down what that means. So 1 to the third plus 2 to the third plus dot 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 plus k to the third is equal to k squared times k plus 1 squared divided by 4. So that's the if part. So again, this part, you don't need to write this down at all. That's just what we're doing. So in step 3, we're actually going to do the proving. So we assume it's true for n equals k. Now what I want to do is consider n equals k plus 1. So I'm just going to start by saying consider n equals k plus 1. So now I'm actually going to erase this little part right here because I want to highlight the consistency here. This is what you will do for step 1. You will start with let n equals 1, show left equals right. In step number 2, you will have that sentence. Assume it's true for n equals k, bigger than 1. And then write down what that means. So a tree with n vertices, or with k vertices, has k minus 1 edges. Or, whatever the thing is. And then this will be the same sentence to start your step 3. So now what we're going to do is be slick. We're going to try to show that it's true for k plus 1 if we assume that it's true for k. We've assumed it's true for k. So what I'm going to do is, like I did in number 1, I'm going to start with the left-hand side, make it look like the right-hand side. All right, but we're going to do something a little slick in here. We're going to let, oh, well, no, we're done with let. So then the left-hand side is equal to 1 cubed plus 2 cubed plus ... plus k cubed plus k plus 1 cubed. So you see what I did? Our n here, we're going up to k plus 1 this time, but I'm going to go ahead and write the 1 before it. Because of step 2, we're going to know what the whole first part is equal to. So do you see the slickness there? Yes? We're good? All right. Well, then this is equal to, well, the 1 cubed plus 2 cubed up to k cubed is k squared times k plus 1 squared divided by 4. I'm sorry, I've got like, okay. So we use step 2, which is called our induction step or our induction hypothesis. We use that to make this nice thing that no longer has a ... in it or anything. Now what I want to do is I want to make that look like this with a k plus 1 plugged into it, right? So you might want to just kind of off to the side see what that looks like. So I'm just going to kind of stick it over here. This is like scratch paper. If I plugged in a k plus 1 to that, it would look like this, right? So that's what I need for mine to look like. So 1 up through n should look like this. We're looking at 1 up through k plus 1, so it should look like that. So if you want to just kind of put that over there, because otherwise sometimes it's hard to make it look like that if you don't kind of see where it's going. So let's go ahead and kind of, I guess, get a common denominator first. Or we could, we have 2 terms here. We could factor out the k plus 1 squared. Let's do it. So I'm going to factor out k plus 1 squared. And it'll look like that. And then if you get a common denominator over there, so k plus 1 squared times, that would be k squared plus 4k plus 4 divided by 4. Make sure I did that right. So I took out 2 of the k plus 1s, which left me with k squared plus, or k squared over 4 plus k plus 1. Then I got a common denominator there. All right, so I'm hoping this is k plus 2 squared. That is k plus 2 squared, isn't it? So this is equal to k plus 1 squared. Notice that's k plus 2 squared over 4. So now I can make it look just like I wanted it to. So k plus 1 squared times k plus 1 squared divided by 4, which is the right-hand side. And we did it. So, I'm sorry, my head's right in the way. So, we made the left-hand side look like the right-hand side as long as the 1 through k part was true. So that's why we assume it's true for k. Prove that as long as k is true, k plus 1 is true. Okay, well, we know that's true then. We know it's true for 1, so that means if it's true for 1, it's true for 2. True for 2, true for 3. So see, this now gets us every single natural number. So make sure you put your conclusion, which I'm going to erase the top here and put in my conclusion. So, by mathematical induction, that doesn't say mathematical, but just pretend like it does. By mathematical induction on n, we know, or we have 1 cubed plus 2 cubed plus ... plus n cubed equals n squared times n plus 1 squared over 4. Mathematical. So it's pretty slick. And sometimes in step 3 you have to do a little bit of fiddling, but notice without knowing what I needed it to look like, why would I have done this? You know what I mean? So it's a good idea to kind of write down what it's going to look like at the end. However, notice what I did not do. I didn't start with the equation I'm trying to prove. So please do not do that. Don't write down what you're trying to prove. Start with the left-hand side. Equals, 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 equals till you get to the right-hand side. Okay? Let's do another one. I only have one example of each type. Yeah, we got to do another one. Let's do... That's the n squared one. Let's do one of the kind of divided ones. So let's do another one of these. All right, we're going to prove that for n greater than or equal to 0, natural number or integer, that, I can't read my handwriting. Is that a 3 or a 5? I think it's a 3. 3 divides 5 to the 2n minus 1. So this one looks a little bit different because it doesn't have like an equals that's going to happen. But we can make it into an equal sign, right? So let n equal, so what's the starting point here? Is it 1 or is it 0 for this one? 0. So we're going to start with 0. So let n equal 0. So then 5 to the 2 times 0 minus 1 is equal to 5 to the 0 what? Oh, okay. Minus 1. I was thinking this was 4, and I was like, 3 does not divide 4. What's 5 to the 0 power? 1, right? So this is 1 minus 1, which is equal to 0. So notice 3 divides 0. So it's true. Right. Everybody divides 0, right? 0 can't divide anybody, but everybody divides 0. All right, so that was step number 1. Now we're going to assume it's true for n equal to k, bigger than 0. So notice that this time I did bigger than 0 because that's the one we already proved it for, right? So last time it was greater than 1 because we had proved it for 1. So now we want to write down what this means. So 3 divides 5 to the 2k minus 1. Now I'm actually going to write this so that it has an equal sign. So this means that 5 to the 2k minus 1 is equal to 3a for some integer a. Did I need to do that? No, I didn't need to do that. But I wanted to. We don't actually use that. Notice the consistency, just like last time. We started with that, then we did this. So now we're going to consider n equals k plus 1. And so what do we actually want to look at? We want to look at that 5 part, right? So then we have 5 to the 2 times k plus 1 minus 1, which is equal to 5 to the 2k plus 2, which is equal to, all right, when you add exponents, what did you do? When do you add exponents together?
What do you do when?
Yeah, when would you end up adding exponents? Like, when might you get that? What would you have started with?
When it's squared plus
Not plus,
times.
times, right? So I guess that my question did sound a little funny, didn't it? So when do you end up adding exponents? When you multiply things together, right?
Yeah.
So we can actually, it's weird for us because we don't do this very often, but see, we can undo this. You see, we can break that up. We don't usually do that, though. Usually we're always putting them together, right? But look what I just did. I now have, oh, so I am going to use it. I have a 5 to the 2k here now. Don't we actually know what 5 to the 2k equals? So we can plug that in using the induction step. So 5 to the 2k is 3a plus 1. You see if I just move the 1 over? Which we can actually, like, do that. All right, what is that equal to? That's equal to, let's see, 25 times 3 is 75a plus 25 minus 1. Now, I forgot what we were doing here for a second. We want 3 to divide this. So, is 3 dividing that okay? So I could factor a 3 out, right? So let's factor that 3 out. And I'm just going to point out here that, just remind ourselves that a was an integer. So, 3 divides 5 to the 2k plus 1 minus 1. We literally just wrote it as 3 times an integer. So this one was a little bit different because it didn't have that whole left-hand side, right-hand side. But notice we still we did the same thing. So when we got to step 3, we wrote out what it would mean with a k plus 1. But then in our algebra, we ended up with step 2 in there somewhere. So you're going to be, if you don't use step 2, something probably went wonky. Right, so you make that assumption because you're going to use the assumption somewhere. Okay, so then we're able to put that in there, and then we see that 3 divides that. So again, a conclusion, by mathematical induction on n, this statement is true. What do you think? Slick? Slick? All right, so let's do the next one that was on the sheet. So this one's actually using strong induction. Oh, whoops. So strong induction is the one where you're going to assume everything up to k. So it just changes step 2 a little bit, that's all. So let's see. Did I write this one down? I think it's this one. Is it the intersection one? Okay, so suppose A1, A2, dot, 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 A sub n are sets in some universe U, and that n is greater than or equal to 2. So we have at least 2 sets. So we're going to show then that A1, is this union or intersection? Intersection. Okay. Oh, forgot the complements. All right. So the complement of intersections is the union of complements. So this is what we're going to show. So now again, we're going to use strong induction here. But first step is always kind of this, well, always the same. But now what's my base step here? So I'm going to start with let n equal what? Perfect. So that's the smallest it can be. So we're going to start with let n equal 2. So then the left-hand side, this one does have a left and a right. The left-hand side would be A1 intersect A2, complement, which is equal to, now you're not using De Morgan's law, this is pretty much what we're trying to prove, but what is a complement? Well, that means the universe minus A1 intersect A2. Which is equal to the universe minus A1 okay, the universe, if you subtract a union, it turns it into the other one. So, oh, sorry, we're subtracting the intersection. So, union U minus A2. So this is the universe minus A1 unioned with the universe minus A2. Well, what is that equal to? The universe minus A1, that's A1 complement. Union, the universe minus A2, is A2 complement, and that's the right-hand side. So it's true. So remember when you distribute this is sets, so it's not algebra, but it's kind of like, you know, if you distribute a negative, it switches the, so. All right, so we know that it's true for the two of them. So now we're going to start making this bigger. So, but using strong induction. So we are going to assume, okay, how did your book put this? Assume it's true for up to K. I never think of a good way to say this. Assume it's true for all let's just pick a different letter. For all M. Oh, whoops, not the 1. That's a 2, right? Okay, so what we're saying is it's true for everything from 3 up to K. You see, we already proved it for 2. So normally we would just say K greater than 2, but we want to say that it's true for everybody leading up to K. So if K was 8, we're saying it's true for 3, 4, 5, 6, 7, and 8. Okay. In other words, so well, that's an M, technically. And now that M could go all the way up to K. Well, I guess I could put a K, but you know, I'm just being a little awkward there. But okay, so now what we're going to do is consider N equals K plus 1. So in other words, what we're looking at, so for our left-hand side, we have A1 intersect A2 intersect ... intersect A sub k, and then we're going to stick on the k plus 1. So notice I'm going to stick the k in there because I know about him from number 2. So that's why I want him there. I don't even think we need strong induction for this one. Whatever. All right, so now what we're going to do is something slick. According to number 2, it's good for 2 things, 3 things, 4 things, 5 things, 6 things, 7 things, all the way up to k things. We know that this thing is true, right? We also know from number 1 that it's true for just 2 things. So what if I were to kind of group these together? This is a set, right? And this is a set. Now that's just 2 things, right? This one intersected with this one. So according to step 1, so I'm just going to put a little 1 here. According to step 1, I can break up 2 things just fine. It's the complement of the first one union the complement of the second one. So you see what we did? We just thought of it as 2 things, and according to step 1 that we proved, the intersection, the complement of the intersection of 2 things is simply the complement of the first one union the complement of the second one. Now, by step number 2, I can completely break the left side up because it has k things in it. And I know this is true leading all the way up to k things, right? So according to step 2, I can say this is A1 union A2 union ... union A sub k complements. And we have our answer, right? And we're done. And we actually could have divided this anywhere. I could have divided like the first M and the second M, and then we knew that we could do the first ones, etc. So, oh, and that's perfect timing. So by induction, strong induction on N, it's true. Yay, we did it.